Hello, everybody. I'm Aris. I'm CTO at DriveTribe, and I'm going to talk to you about how just a handful of people built a scalable social network using Apache Flink. As a preface, DriveTribe is the world's biggest motoring community, essentially a social platform for petrolheads, and it was founded by those three good-looking gentlemen, Jeremy Clarkson, Richard Hammond, and James May. At the core, DriveTribe is a content destination. Users consume feeds of content, images, videos, long-form articles, quizzes, and so on and so forth. And the content is organized in homogeneous categories called tribes. And different users have different interests, and the tribe model allows us to mix and match and create a nice and personalized experience. One example, as we see there, it's like Porsche enthusiasts, but there are other people that are into drifting or motorcycles or luxury vehicles and so on and so forth. Let's now focus on a single piece of content and try to analyze it from a technical perspective. This is a single article by Richard Hammond and contains a plethora of content and engagement information. And there is a question, what kind of data do we need in order to compute an aggregation like this? Well, first, we'd have to get the user, we'd have to get the user tribes, then we'd have to get the actual content of the article. In this case, it's a video and some text and maybe a few images. Then we would have to count the number of views, count the number of comments, and count the number of likes. And it's highly unlikely that this will ever appear on its own without some kind of surrounding context, which most probably, in most cases, this is a feed. So we'd have to rank a bunch of them for a specific user and then execute all of those queries multiple times for each single one of them in order to render like a page in the feed. So at the high level, this is the technical challenge that we have. Personalized feeds of content containing complex aggregations, and that's a pretty common problem in social media, like Facebook, Twitter, everybody has a problem similar to that. So before deep diving into any kind of solution, we need to set a few prerequisites. The solution has to be scalable. Jeremy Clarkson has over 7 million Twitter followers, so we cannot really hack it and worry about scalability later. Has to be performance, low latency is key, mobile networks are really slow, they're adding quite a bit to it. Has to be flexible because startups tend to iterate a lot, it's difficult to get it right the first time around, and has to be maintainable as well because spaghetti code works a bit like interest on debt. So naive approach would be to start with something like a three-tier architecture that people are familiar with, where clients interact with a fleet of stateless servers, also known as the API or the backend via HTTP, which is a stateless protocol anyway. Those perform simple tasks like access control, view composition, etc. And whenever there is something that they need to remember for the future, they use a database, which is essentially a global shared mutable state. Simple approach would be to just store all the data there and then compose those aggregated views on the fly at read time. For the example of the article that we have, that would look a bit like that. We'd have to do 3 GET queries to get the user tribe and the article. Those are simple key value accesses, and that would be fairly quick on any kind of database. But then we'd have to perform 3 count queries, and especially for the views, if we have 360,000 for this particular instance, and we have 1 million of those, you see how we have a gigantic table, and in most cases that has a linear time complexity to compute, which can be very expensive. What makes things worse is that we have to execute those 6 queries for every single item in the page. And that's excluding costs of personalization and ranking, etc. That's quite some work to do at read time. That would be probably slow, not really performant. It would be very expensive to scale as well. Well, the first optimization we could do is to aggregate at write time. Right? We get some data from the API, and then we perform the aggregator. We compute those counters, we store them. So whenever the client requests a page, that's already there. We have some form of article view that's already there, and we can fetch it. For the like example, we just get the like, store the like in the database, and then update those counters. And then we get a request to compute a feed of those counters already materialized, and they're ready to be served. However, the problem is that as the project evolves, we get additional requirements. For example, we may want to send notification every time we get a like. Or we may want to maintain some form of author stats to find the best authors that we have in the platform. Or we may just have other technical issues. For example, we may have some caching mechanism, or we may use a different database for search. Or there are other cases where we need to fan out. The users can update their usernames, and if they have authored 1,000 articles, we would need to update 1,000 rows, some form of hypothetical database with that thing. So that sounds a bit like a recipe of disaster. So a simple user action is triggering a potentially unbound sequence of side effects, many of which require network I/O, and they can fail. So what happens if one of them fails in the middle, or if the server crashes, etc.? So we may end up like sending a notification but not storing the like, or we may end up updating half of our articles and not the other half, etc. And we have like inconsistent data in the end. Other problem is concurrency. We may have like 20 people liking the same article at the same time, and that entails some form of race condition in the database. And the problem is that those state mutations are also destructive and they cannot be undone. So if you have a bug in the logic that updates those statistics, which is a simple example, the data will be corrupted and that will stay there permanently. It's difficult to fix. And we have another problem, that we are coupling the read and the write models, so model evolution becomes very difficult, and migrations are scary, nobody wants to deal with it. So that doesn't seem to be neither extensible nor maintainable. It seems that we have all of those really horrible side effects by coupling data injection with data processing. So let's take a step back and try to decouple things and think of like a better solution. Clients send events to the API, like John liked Jeremy's post, and Maria updated her profile, etc. And those are immutable. They capture a user action, happened at some point in time, and they're a really rich way to represent our data. Like liking something and unliking it is not the same as not doing it in the first place, right? So every application state instance can be modeled as a projection of those events. So the first thing we can do is just persist all of those events in a log and have an append-only immutable log of events. Then we can implement a piece of code, let's call it the event reducer, that can create those application states instances on the fly. And because the log is immutable, that can happen even retroactively. And this is essentially event sourcing. Another nice side effect is we're not forced to use the same model at read and at write time, which means we can decouple the two of them and optimize every single path of the system separately, and that's essentially CQRS, is command query responsibility segregation. Putting everything in a system, we would get the likes from the clients, and then our API, the only thing we have to do is to just store the like in the log. And then the first set of requirements that we get is to compute a few statistics. So we can implement a piece of code called like the article stat reducer that does just that. Then we need to send notification. Good, we can implement notification reducer that will integrate with SNS or any other external system. I will just do that. We need to compute stats. Again, the raw data is already there. We can even do that retroactively, and so on and so forth. As requirements change, we can add and remove those modules on the fly. We can troubleshoot them independently. We can optimize them independently, and so on and so forth. So we get modularity, and you get composability out of this architecture. So when a request like fetch a feed comes in, because we have already prematerialized our views in a nice way, the performance is going to be as good as it gets, as good as our database is. So how does this compare with like the initial problems that we had, the initial checklist of issues that we had? Well, it's fairly extensible and fairly maintainable because the ingestion and processing logic are completely decoupled. And since we can compose the various stream processors together into a solution and just remove a few, add a few according to our needs, it seems that we can scale our code base without having to decouple things every time. As far as performance is concerned, well, we have materialized views already in the database, which means that we can fetch and sort everything in a single query. And as far as atomicity is concerned, well, the semantics change. Because the log is immutable, it means that we can process it as many times as we want, which means that unless something catastrophic happens, for example, there's a hurricane that wipes off AWS in Ireland, then all of our messages will be eventually processed. So we have like an asynchronous, eventually consistent system, which will solve the problem of trying to do everything in a single go, like in a strongly, immediately consistent transaction as we would in a SQL database, for example. Different semantics, but at least we can guarantee that eventually our system will be consistent. So how would we go about implementing something like this in practice? Well, first we would need a log to store our data, and for that we have chosen to use Apache Kafka. It's like a distributed fault tolerant, it's durable, it's very fast append-only log, can scale to thousands of nodes, producers, consumers, etc. We use for every business entity a topic, and it's a source of truth of the system, which means that every view that we have can be built by reprocessing the data we have in Kafka. Then we would need the stream processor, and we have chosen to use Apache Flink, because it's scalable, it's mature, performant, really elegant high-level APIs in Scala, powerful low-level APIs for advanced tuning, and multiple battle-tested integrations with systems already out there, like RabbitMQ, Kafka, various things like Cassandra, Elasticsearch, etc., and very nice and active and supportive community. And we need a data store as well, and we have chosen to use Elasticsearch because it's horizontally scalable document store, really rich and expressive query language. And the good thing is that it's dispensable. This is not the source of truth of our system, which means that if we find another data store with better characteristics, we can just replay the log through our stream processors and have a new data store in place. So as a system, if we put everything together, it looks a bit like that. We have a bunch of stateless API servers written with HTTP in Scala that store raw events in Kafka, and then in Flink, we have various reducers that consume those events, produce aggregated views, store them in Elasticsearch that are ready for consumption. The good thing with the architecture like that is we do not really have to wait for the client to fetch the data, which means we can have a WebSocket connection between Flink and the client, and whenever there is new data available for any particular user, we can just push them and make the application feel interactive and a lot more alive. However, there are a few issues running an application like that in production with this architecture. First, Flink is stateful, right? It serializes data, stores the data in RocksDB, and scheme evolution is not really supported out of the box, which means that if we make incompatible changes in our program, we may have to replay the log to recreate the state in Flink. And that's a bit of a problem in a running system. Additionally, we have to treat Elasticsearch in this instance as our main data source. So if we want to upgrade it, we cannot really take it online, upgrade it, or remove it completely, etc. So we just thought that the only core part of our architecture is the log where we store our data, and it's Kafka. So by automating the provisioning of all the components, we can just create, like, really quickly a mirror of the system, deploy our code there, and then run a few automated checks. And then by just switching the load balancer from the active side to the inactive side, we can do continuous deployment in a really complicated architecture. And it's very easy to actually share checkpoints between the two, so we can seed it and do it really quickly. So at this point, my colleague Alex will walk you through a real-world code example of implementing an application on a system like this.
Hi, so my name is Alex, and yeah, as Aris said, he gave a bit of an architectural overview of what our application, what DriveTribe looks like. I'll be focusing a bit more on what the code would look like in such an application. So I'll be talking a bit about the trade-offs that come paired with this kind of architecture, and how we can mitigate those with some tools that we can take from functional programming. So yeah, let's look at an example. So as you can see, we have a post, and users they can bump a post if they like it, and yeah. So let's have a look how we can implement this counter. So we basically want to count how many users like a post. While implementing this, we want to keep a few principles in mind. We basically want to achieve 3 goals. First is modularity. So we basically want to have code which is general, which we don't. So in this example, for example, you can see that we want to count the bumps, but we may also want to count the comments or the views. So we want code which is reusable, which is generic. This is basically the don't repeat yourself principle. Then we want our code to be testable. We want to make sure that we can verify that the code does what it's supposed to do. And third, and finally, we want the code to be concise. We want to be able to look at the code we wrote a month ago, and want to know that it should be easy to read and to reason about it. Okay, so let's talk a bit about the architectural trade-offs. So as Aris said, architecture is completely asynchronous. That means that basically every step you see in this diagram is asynchronous. So the like event is sent to the API, which is appended to the log. So this event is appended to the log asynchronously, then it's picked up by the reducer asynchronously, and it's persisted asynchronously. So while this event is in flight, it means that our API cannot observe that this event has happened, right? Because it hasn't reached the DB yet. So that means that we can't reject any duplicate like events. So that means that in this architecture, eventually we will have some duplicates in our event log, despite exactly what semantics that Flink may give us. So how can we solve this problem? So let's first define in code what our problem looks like. So let's model it out first. So we have a like event, which contains a post ID, a user ID, and a timestamp. Then down there in the reducer, we can see that we have a stream of like events. Basically, what we want to do is we want to accumulate the likes with a stateful operator and want to count the number of users who like a given post. So this state is modeled as follows. We have an ID of a post, and then we'll come up with some kind of counter that we can use. Then in the end, we will emit this state so that it can be indexed or stored in some kind of database. So yeah, first attempt, how do you usually count stuff? Well, with numbers, right? We want to count big numbers, so we can use longs, and we can simply add longs together to count, right? So essentially, we need to do two things. We need to transform our like event into some kind of state. So that's done on the second line. We have the supply method, which takes a like event, transforms it into a post state by taking the post ID and just counting one, basically. The second thing we have to do is we have to be able to combine those two states. So essentially what we do is we take a post state and we combine it with another one. We take the ID and we just add the two counters together. So we're adding longs, basically. Yeah, so what would this look like in our reducer? So we have the like event, we transform it, we map it to this post state. Then we key by ID because we want to aggregate by post ID, right? We want to count the number of users which liked a given post ID. So aggregation happens on the post ID. And we can simply use our combine method, which we've defined before, to take the old state, combine it with the new state, emit this event, and to keep it in the state for the next event to come in. So in this case, we're using longs, right? So what would happen if we have duplicate events? So like we said, every event is counted distinctly. So that means that if we have duplicate events, we count them in a duplicate fashion as well, which means that we end up with the wrong result, right? So essentially what we want to do is we want to count a distinct number of users and not just events. So do we know of any data structure which can handle such deduplication? Well, yeah, we could use a set, for example. So what we would do is we would replace the state with a set instead of a long, and we would keep track of all the user IDs, and the set would assure that we don't have any duplicates. So basically, the operation that we do now to combine two post states is to take the set union of the two. So the set union is idempotent, which basically means that, as you can see in this example, if you do one operation twice, so in this case, you add the set of two to a set of one twice, it ends up the same as just adding it once. So that way, we get rid of duplicates. And then if we want to get the count, we can just get the cardinality or the size of the set. Okay, so we've seen two different solutions. We said that we want to have general code. So how can we generalize this solution, right? So we had two similar approaches, and both had a combine method, which we can call like a plus operator. And essentially, we can look at the desired properties of our system, and we can come up with two properties that we may want to achieve. So the first one is associativity, which means I can combine things from the left, or I can combine them from the right, and the results will remain the same, which essentially means that you can parallelize your computation into smaller chunks. Each process calculates its subproblem, and you can recombine them again. And you can basically arbitrarily chop up your computation anyway. It will always result into the same solution. So this is data parallelism, and then we want the idempotence, like I've explained before. This is useful for deduplication. Yeah, so if we look at maths, we can find something called a band algebra, which satisfies these exact properties. So what does a band algebra correspond to in programming? Well, it's basically a type with an API. So in functional programming, we would call this a type class. In object-oriented programming, we would call this an interface. And the second thing it has to have is a set of laws. So like we said before, we want associativity and idempotence. So in Scala, a band would look something like this, right? You have a band of type T, where you have a combine function, which takes two T's and combines them together, resulting in a new T. Yeah, so we've modeled our state as a post state case class, right? So does that form a band in itself as well? Well, if you assume that the IDs of two post states are the same, so you remember we were aggregating things based on a post ID. Well, in that case, yes, this combine operator does form an algebra, and its implementation, its definition, you can find there. So basically, when we use a set for our post state, we just do the set union on the two counters. We replace the ID with the post ID, and we have a band basically. And yeah, so we have an example here where we have two post IDs with two different user IDs which like something, and if we combine them together, we get we basically have the set union. So this property also holds for this bigger type, which is the post state. Cool. So how would this look like in the reducer? So it's basically the same thing. We've kind of abstracted out this combined thing. Instead, we're using this band algebra, so we can use this operator to combine these things together. So it's basically the same. We just map something to this post state. We key by ID, and we just use this operator to aggregate this stuff. Cool. So we've been using a set so far. We've seen that the band satisfies our properties to solve our problem. Can we use, can we improve this? Well, the problem with the set is that it has a linear space complexity, right? So we can just look for a different band, replace our set with another implementation, and that should be it. So an hyperlog log, for example, is an approximation algorithm where you can approximate the size. You can basically count with an error. And this uses constant space complexity. So this also forms a band, so we can just simply swap out our set with this hyperlog log, and we're basically done. So yeah, going back to our design goals, we said we wanted to achieve modularity, testability, and conciseness. So like we said right now, modularity is achieved now because we've kind of focused on the properties of the solution, not on the implementation of the solution itself, which means that we just look for a different solution with the same properties, and we can just swap them out arbitrarily. And we know that the properties still hold, so that's a nice property, and that basically means that we have modular code because we can swap out one component for another, and we know that the properties that we want to achieve still hold. Cool. So we satisfied modularity. So the next thing is conciseness. Well, in Scala we have this thing with implicits where we can pass stuff around implicitly. So with a bit of implicit plumbing, we can make this code very very concise. Basically, we can define a combine, which we can call on the key stream itself. So what that does is it just reduces. So it takes an implicit instance of this band. It just calls a reduce function on this key stream, and it just combines those things together with your band definition. So then the solution would look something like this. We have to provide an instance of this band, and we can simply map our like events to a post state. We can then key it by ID, and we can just simply call this combine function that I've just defined to aggregate everything together. We get this aggregated post state, and that then gets emitted to our database or whatever. So conciseness, looks fine. The last thing was testability. So we said that we're focusing on properties instead of implementations, right? So we can use some tools from functional programming to do testing. It's called property-based testing. So in Haskell, there's a library called QuickCheck. In Scala, there's something called ScalaCheck, where you basically generate random inputs of random data of your type, and then you can basically check your type, whether your type has certain properties or invariants. And so basically that looks something like this. So there's this library in Scala, which is called type level cats, where you can simply say, for my type, which in this case is post state, I want to check that all the band laws hold. That generates all the data, and it generates random data, and verifies that all the properties of the band algebra hold. So cool. I mean, we've looked at one specific algebra, which was the band algebra. But in reality, there's a plethora of different algebras. So if you look at the library called Cats, and Scala provides a complete algebra hierarchy. And so there are a few other examples, like for example monoid, in which you can represent empty values. And you have things like semi-lattices, where you can aggregate out-of-order events, which is essentially what a CRDT is, so a conflict-free replicated data type, which is used a lot in distributed systems. If you want to dive deeper into these kinds of things, there's lots of advanced stuff you can do. So you can basically automatically derive algebra instances for any case class in Scala. So you can just say, I have a case class, I want to derive a band algebra, for example, for this case class. With some type level trickery, you can do all of this automatically without any code, without any boilerplate. Doing lots of other stuff as well. So for example, we have ways of merging streams together by using coproducts and semilattices, which basically gives you an algebra to take separate streams and just merge them together into one big state without having any boilerplate or anything. And yeah, there's some interesting literature on this stuff as well. So there's a paper where which illustrates that with the monoid algebra, you can just rewrite the whole analytics engine based on that simple monoid algebra. So yeah, that's it. Do you guys have any questions for us?
No questions? Any takers? So more of a kind of historical question. How long did it take you guys to kind of evolve to this final state of architecture? Like, did you iterate through the earlier states, and what was that process like? Or, is this something that you just saw up front?
We kind of built that from scratch. So we knew from the beginning that we wanted to build something extensible and scalable because the founders are extremely popular. So we knew we'd have traffic, but we didn't know how much. So we thought that we have to build something scalable to begin with. And it was really clear from the early stages that we have to adopt a blue-green type of deployment architecture to be able to have like a proper CI/CD pipeline on a system that is based on an event log.
Any other questions? What database you guys are using? What database you're using?
We're using Elasticsearch and a bit of Redis to read stuff, depending on the use case.
Okay, so do you have a use case where you don't have to go through Kafka and your reduce algorithm for updates, and how do you deal with those scenarios?
The only use case that we don't use Kafka is for media uploads. For example, there is a user uploading a 1 GB video, and that will go directly to S3 from the API, so if it fails, they can upload again, because Kafka isn't really built for long streams of binary data, but everything else grows through that pipeline.
Thanks.
Have you considered to use the queryable state?
We have thought about that. The only problem is that it is not highly available. So currently, as it stands, because it is not replicated, if you lose the task manager, you just lose the ability to query your data. And because Redis, it comes as a service on AWS and it's quite stable, it's just easier to use a Redis sync, put everything there, etc. But as a concept, it sounds extremely interesting, because the stream processor can compute the data, can store the data. So if you can expose the data via querying API, etc., that would be amazing. For example, if you use a Lucene index at every task manager, then you can have a streaming kind of version of Elasticsearch on Flink, which is really interesting, but I don't think Flink is there yet to support something like that.
Thank you.
Any other questions? Cool. Okay then. Join me in thanking these guys for their talk. Thanks very much.
Yeah, thanks, guys.
Thank you.